So now that we've had a chance to talk about Volatile and you've had a chance to see an example application, let's kind of take a step back and talk about some of the usage considerations to think about when you are deciding if you should be using Volatile or not in your program. So you should use volatile variables sparingly. And in particular, you want to make sure that you don't abuse busy waiting. So we've talked about busy waiting before. Busy waiting is this sort of neurotic checking of a volatile flag in a loop, in a tight loop. And if it turns out that you're doing this and the loop body doesn't really do very much work, so you're just spending a lot of time spinning, then you can consume a lot of CPU time or core time unnecessarily. Now, again, I think I mentioned before, there are situations where that's perfectly acceptable. If you absolutely have to find out the nanosecond that something changes its state and react to it, then it's maybe a good thing to do if you're monitoring the temperature in a nuclear reactor, for example. But oftentimes that's probably overkill. And so you just have to be careful you don't spin in a way that will cause excessive CPU consumption for no particular benefit. There are some situations where busy waiting is useful, however, but for the most part, you probably don't want to have to know or care about that. So the best way to use busy waiting is to leverage existing Java synchronizers, such as the mechanisms that are available in the Java class library, in particular in the Java util concurrent package. And if you watch the video here by my good friend and colleague, Doug Lee, he talks a lot about how they designed the Java concurrent packages and why they did it the way they do, and why it leverages features on modern multi-core processors in clever ways that the average programmer really doesn't want to know about or be aware of. They just want the whole thing to work on their behalf. By the way, an interesting question is, why do we teach this class in Java as opposed to, say, C or C++? Well, it turns out that Java has a very, very powerful set of concurrency mechanisms in terms of all the different synchronizers, all the different threading mechanisms, threading frameworks. And that's just classic Java. That's just the stuff we're covering in this course, the concurrent object-oriented portions of Java. If you take a look at the more modern features in Java, things like Java parallel streams, if you take a look at Java completable futures, if you take a look at reactive streams like RxJava and Project Reactor, you'll see that there's even more cool capabilities that are available and have been around for a very long time and are fairly straightforward to understand and apply in a good portable manner on lots of different platforms. So that's why we're doing this class in Java. I've also been programming with C++ for a very long time and have a lot of experience with concurrent programming in C++. But in my experience, the Java features are just a little bit better thought out at this point and are much more mature and have been much more mature for a long time. The good news is that modern versions of C++ are getting better in terms of their support for concurrency, but they're still not quite where Java is, and certainly have not been until very recently in terms of support for things like concurrent containers and concurrent collections and so on. Okay, so one of the things to remember when you start dealing with Volatile is that complex operations that perform multiple instructions cannot use Volatile by itself. In particular, if you have code like this, where you've got some counter variable that's volatile, and in one thread you increment the counter, and in the other thread you increment it or decrement it or do something to it, be aware that those incrementations or decrementations are not atomic. In particular, if you increment a counter, it loads the contents of the counter memory variable into a register, increments the register, and then stores the result of the register back into main memory. And those are 3 instructions. And so if you have another thread doing the same thing at the same time, those instructions can interleave, and probably will interleave at the most inopportune moment, and you'll end up with inconsistent results. And that's what we talked about earlier in the context of these so-called write-write conflicts. And so you can end up with very strange results where writes get overwritten and lost. You have the lost write problem and so on. So if you find yourself needing to do things like increment or decrement individual variables, don't take your chances. Instead, use the appropriate atomic variant. So use atomic long or atomic integer or whatever type of atomic you need to get the job done. And you'll find that that will address the types of problems you see here. Another thing to remember, this is also very subtle. Defining an array or an object as volatile only makes the reference volatile. It does not actually make the contents volatile. And see, for example, here's the vector implementation that we have with Java. This is just Java's vector. And you can see internally it's got an element count and element data. And then down here we say volatile vector V. Well, what's happening here is V is made volatile, but it was already volatile because references are already volatile. So that's kind of a belt and suspenders approach. And what that's not doing is that's not actually making the contents, element count, element data, and so on. Those things are not made volatile by making the reference volatile. And as a consequence, these are non-volatile fields. Well, that may raise the question in your mind, well, how the heck do we know that those things don't get corrupted when methods are called? And it turns out that the way that that's solved is by using other Java synchronizer mechanisms, such as synchronized statements or synchronized methods. So for example, if you were to take a look at the set method on the vector that comes out of Java, then what you can see here is that it's defined as a synchronized method. And what that means is only one thread of control can be calling the set method on a given instance of vector at the same time. So it's a fancy way of saying that set is now mutually exclusive. So only one call to set can be occurring in any given thread on the same object. Now, of course, if you have 2 or 3 different instances of vector, then different threads could be calling set on those different instances. That's not a problem. But for a given instance, it means that only one thread of control at a time can be in the critical section, which in this case is defined as the entire method body. So the checking to see whether the location is less than the element count, the read of element data, the write to element data, and so on and so forth. All those operations are going to be atomic, even though they're occurring on shared mutable data or shared mutable state, because the synchronized method and the synchronized keyword will cause the compiler to generate code that uses low-level virtual machine calls to ensure that that region of code, that so-called critical section, is given mutually exclusive access by the thread that owns the intrinsic lock, which is just the name of the lock that's dealt with synchronized in the way it's done here. So going back to some other questions people had asked earlier, what's happening here is that if we have to protect a broader scope or span of code, then we can use synchronized mechanisms like synchronized statements, synchronized methods, or the Java synchronizer classes like reentrant lock or stamped lock and so on, in order to be able to get mutual exclusion and atomicity and visibility and ordering and so on over these critical sections, which are something that span more than a single read or a single write. Another thing to note here, which is sometimes a little confusing to people who have grown up with C and C++, is that the semantics of volatile in Java are not the same as they are in C and C++. And this tends to befuddle a lot of programmers who come from other backgrounds, namely C and C++. In C and C++, volatile variables are not atomic, and therefore they don't create these so-called happens before relationships that we talked about earlier, and we'll cover in more detail later. Instead, volatile is just an indicator to the compiler to disable compiler optimizations. And it says, even though it may look like I'm reading and writing to a variable multiple times in a block, don't optimize this away, because those variables could be mapped to things like hardware registers that are being dealt with in some other way, and don't optimize away what looks like redundant code. So just be aware that if you run across C and C++ developers and you talk to them about volatile, they may not have the same mental model that you do once you understand how it works in Java. So that's the end of the overview of Volatile. We'll be using Volatile in other parts of the course. You'll get a chance to do an assignment with it later. So it's important to understand how it works. It's actually very simple, but because it's so simple, it's also easy to think it does more than it really does. So always make sure you're aware of the usage considerations if you decide to use Volatile in your Java programs.